Welcome back, everyone. Today, we will be continuing our deep learning playlist. And in the last video, we've learned everything we can know about perceptron. So, if you haven't seen that video, make sure you go check that out. I'll put a link to it on the top right. You can go access it, watch it, and yeah, let's just get started. Today, we'll be taking a look at something called as activation functions. So, now before we go into activation functions, I want to talk about something. In the last class, we have seen problem with a single perceptron, which is called the XOR problem. So the graph of it looks something like this. These are classes zeros, and the blue ones are classes ones. And we saw that in perceptron, we won't be able to draw a straight line which can classify both which can separate both red lines, red dots and blue dots. So how do we fix this? Now, how do we go from something which can only draw straight lines, so which can to something which can recognize faces, something which can understand language, generate art, etc. So the answer for that is activation function. So today we'll understand exactly what activation functions are, why they are used to make neural network. Yeah, so let's just get started. In the previous video, we have seen perceptron. Now, how does a perceptron look? It looks something like this. It takes multiple inputs, let's say x1, x2, x3, and it gives a singular output. And this is perceptron. Each input will have several weights, w1, W2, W3. Now, what is the step? First step, it will take the inputs. Second step, it will multiply each input with their weights. Now, the third one is whatever output we'll get, it will make a decision based on the output, right? So, this third step, whatever we have here, this is the main playground for activation function. Whatever weighted sum we have, for example, W1 x1 plus W2 x2 plus W3 x3. This one is usually not enough for us to make a decision. So, whatever decision we make is dependent on the value of this. Now, making a decision with this is the job of an activation function. So, it takes that weighted sum and it will transform it into an output. So, it basically answers the question, given this weighted sum, what should be the output of my neuron? That is the only question which activation function will answer. Okay, so we'll take a small analogy so that you can easily get why we are trying to do this. So you can think of it like this. Okay, so this weighted sum, whatever we have right here, I will just write it down here once more. W1 x1 plus W2 x2 plus W3 x3. Now, whatever weighted sum we have here, think of it as like gathering evidence. Okay, so you're gathering all the information of x1, x2, x3, and their corresponding weights, how much they are important in the output, and you're adding it up. So that will, let's say, give you a score. It is just giving you a score. Now, this raw score isn't always useful. You have to interpret that score, and the activation function is your interpretation rule. So, I'll just give you a small analogy. So, imagine you're deciding whether to go to a coffee shop or not. Okay. So, what do you decide it on? You'll see how good is the coffee, or how far away is it, or how expensive is it, and do they have, say, Wi-Fi? If you consider these four things, and each of them will have, let's say, you give more importance to how good the coffee is, so +8, and how far is it? It is very far away, so maybe you have the importance as -3. It is slightly expensive, so -2, and Wi-Fi, they do have Wi-Fi, so you do it +5. So overall, your sum will become +8, right? Now, this means your activation function will interpret this value of 8 as, let's say 8 is positive, so we can go to the coffee shop. Or let's say 8 is very high, so there is a 99.7% probability that we can go to the coffee shop. Or 8 is positive, so just pass it on through and you can go. 8 is high, so definitely yes. So something like this. How do we interpret the value of this 8? Is what activation function does. Now, different activation functions will give you different interpretations for the same evidence which we have right here. So it is very crucial to select proper activation function so that your data is represented properly. Now, here we'll talk about math slightly. So whatever we have seen so far, that is called the weighted sum, right? We multiply the values of inputs with their weights. That is called as a weighted sum. Now, weighted sum is W1 x1 plus W2 x2 plus W3 x3 plus so on. And then for each perceptron, we'll have a bias term. Now, if you don't know what a bias is, we've discussed it in the last video. So I highly recommend you guys go check it out. That would be linked in the description as well. So that is W sum. Let's just name this as Z so that you don't have to write the whole thing every time. And activation function is just as simple as writing f of Z. Now, this will be your output of the neuron. This f can be any activation function, any function which you want. So, the whole workflow of it would be in this way. So, you'll have an input, okay, that will go through the weighted sum. After going through the weighted sum, you will go to the activation function. After going to the activation function, the whatever output will be there, that will be provided to the output flow. Now, we'll just draw a simpler diagram of our neural network. So this is our this is our perceptron, not a neural network. So this is our x1, x2, x3, w1, w2, w3. Now this is a this block will represent our weighted sum. So I'll just say that this is Z for now on, whatever we have. And whatever output we get of Z, this will be passed on through a function. This function is the activation function, which we have right here. And through this function, whatever value we get, this would be considered as the output. So this is the overall perceptron model, which a lot of people draw. And now I think you have a clearer understanding of why each thing in the perceptron model exists how it is. Okay, so the input will flow through from here. I'll just mark it in red. Input will flow through from here, and through that it will get weighted sum, and through that it will be scanned and passed through the activation function, and through that the output will be given. Okay, so now you know what activation functions are, but it is crucial to understand why we need them as well. Why do we need activation functions? Can't we just use the weighted sum directly instead of interpreting in a different way? Now, there's few reasons why we should do this. The first reason, and the probably the most important reason, is non-linearity. Now, non-linearity is the most important one because without non-linear activation functions, neural networks are simply useless. So I'll show you why. Okay. So let's say you have two perceptrons. For simplicity, I'll just take one input for now, x1, w1, and the bias of this will be b, and this is the value of z. Okay. Now, without a activation function, this would be the output of the perceptron. Now, let's just say you have another layer with another perceptron. So the output of this perceptron will be the input of the second perceptron. So this would be z again. Okay, and this value would be the output. I'll name this B1, I'll name this B2, two biases. And since this is the weight of this, let's just give this input a weight as well. So that is W2. Now, if you want to write this into a proper value, you can see Z1 is equals to W1 X1 plus B1. Z2 is equals to W1 Z1 plus B2. Right. So this would be our output functions, which with the Z2 will be our final result. And now Let's just take a look at these both equations. Okay. Now, if you see these both equations, you can notice that you can substitute the value of z1 in here. So let's just do that. Z2 is equals to W1 into, oh, this is not W1 by the way, this is W2, my bad. This is W2 because the weight of the output of Z1 is W2. So this is W2 into W1 X1 plus B1 plus B2. Now, if we simplify this, this will become W1 W2 X1 plus W2 B1 plus B2. If you take a look at this equation right here, this is still in the form of Wx plus B, right? W1, W2 being the weights, X1 being the input, W2 is also being the weight, B1 is a constant term, so this whole thing will become a constant, and this is also a constant. So it still is in the form of Wx plus B. Or if you take a look at this equation, it is much easier because you can think of this whole term as a big X. So it still looks in the form of a Wx plus B. Now Wx plus B, we've seen in the previous videos that this is an equation for a straight line, right? Why? Because we have a singular degree of 1. Now, no matter how many layers you stack over and over and over after this, one after the other, one after the other, no matter how many layers you have, it will always be simplified into another linear function, right? So without activation functions, this 100 layers, if you even add 100 layers of this, let's say, perceptron, it will still be equivalent to a singular perceptron. All those layers will become useless because they always collapse down into a singular linear function. No, that's why we would need something called as an activation function. Now we'll modify this with activation functions. So let's say you have layer 1, which is a1 is equals to f of w1x plus b1, and a2, which is the layer 2, is function of w2a1 plus b1. Now f is something which is non-linear. Okay, so you cannot simplify this. You cannot simplify this. Each layer will have some of the other complexity because a1 might have a function f, a2 might have another function f, which can add to the complexity of it. And this is how you generate or build up the ability to learn. Okay, you should need that non-linearity in your activation functions so that it can fit to your data properly, it can recognize your data properly. Now that is the first reason. The first reason is we have a way to introduce non-linearity into our perceptron. The second reason is it will introduce boundaries or ranges in our perceptron. Now what do those mean? So we've seen this example right here of the coffee shop. Uh, Here we have seen that you're given a value of just 8. Okay, but what if I want to make a decision in such a way that my value will stay between 0 and 1? Okay, so let's say you want to find the probability of a person going to this place. In that case, the value of 8 is not that helpful to you. Why? Because 8 is very difficult to convert into a probability state. So in probabilities, every value will stay in the range 0 and 1. Okay, so you want to convert the value of this 8 into something which is 0 and 1, something between 0 and 1. Now this, whatever you have, this is the job of an activation function. So with activation functions, you can bound your outputs, whatever you have, in certain ranges. So I'll give you a few examples. There's an activation function called sigmoid. This activation function will help you bound your range from 0 to 1. Okay, it is perfectly probabilities. Or there's another activation function, anh. This will help you map your output between -1 to +1. Now this is good for zero centered data. And the other one, which is most famous, is reloop. Now this will help you map your data with either 0 or positive. It will eliminate the negative side of the activation function. So without activation functions, your outputs can either go to infinity or it can go very back to 0. So this activation functions will give you control of how your data should actually look, how your data should actually be processed and they'll help you give control. Now, the third reason, we will learn this as we move on, and we learn about back propagation. But most of the activation functions are here differentiable. Okay, so this will help us, do gradient based learning. Now, if you haven't seen my video where I taught about gradient descent, don't worry, we'll cover about gradient descent and everything, vanishing, exploding gradients, in this crash course as well, in this bootcamp as well. So if you haven't checked that out, I highly recommend you go check it out. But if not, don't worry. We'll cover it in more detail when we talk about backpropagation. So for now, you just need to know that if you have smoother activation functions, it is very easier to train and it helps learn properly. So yeah, I think that's pretty much it for this video. I wanted to give you guys a clearer understanding of why we need an activation function. So in the next video, we will go through some examples of activation functions, and we'll visualize an activation function so that you'll have a set understanding of how do activation functions work, how do they look in the graph, how do they map stuff to ranges. So if you guys did like this video, make sure you go smash that like button, hit subscribe, and I'll see you all in another video.